Now we're going to move from measures of location to measures of variability. In order to understand variability in our data, we first start with something called the range. This is the easy one because all it is the highest observation minus the value of the lowest observation, and you end up with the range of where your data is going to be in your sample. In this case, I've provided you some data I got from the textbook where the home sales data in Cincinnati, Ohio, in a suburb in Cincinnati, is as follows. You got 12 homes there ranging from $138,000 to $456,250. To compute the range, you take the largest home sales price, $456,250, and then you subtract the smallest home sales price, $108,000, and you end up with the range, which in this case is $348,250. Now, there's a drawback to doing this. The drawback is simply that the range is based only on 2 of the observations and can be highly influenced by extreme values. So you may have a home in there really for $1.6 million. Think Lake Minnetonka for a second if you're here in Minnesota. If that's part of your data, and then you've got a home somewhere, let's say for $108,000, now your range is somewhere in the neighborhood of $1.6, $1.8 million. Does that really give you a good picture of all of the home prices or the set of data that you have on home prices? Maybe not. But we're going to figure out how to understand what we really have in a minute with some other measures that we're going to take a look at. The first measure of variability we're going to look at outside of range is now going to be something called variance. Now, variance is an interesting topic because what it does is it tells you, with all of the data observations you have, how varied they are amongst themselves. And when we look at that, that's going to tell you whether or not you have data that's very similar in observation, or you're going to have very diverse data in your observations. So you say, okay, well, explain to me, how do I figure out this thing called variance? Here's what you do. You have 2 types. If you have the entire data set for all the things you're observing, and you're trying to figure it out for that, that's called the population variance. But like I said before, we do things with samples in statistics. So sample variance is really an important one to learn as well. So how do you figure that out? Well, here's what you do. Remember the mean that we talked about earlier? Well, what you have to do is you have to take each observation, you subtract the mean from it, then you square that number or that outcome, and then you divide by the number of outcomes. Now, when it's the population variance, you just simply divide by the number of outcomes to make sure that you've got an accurate result. However, when it's the sample variance, we divide by the number of outcomes minus 1. That minus 1 helps with the fact that you're working with a smaller set of data, and it helps to get to a more accurate outcome. So you've got the sample variance, which on the slide you see S squared is equal to the summation of all the observations minus the mean squared divided by n minus 1. And then you have the population variance, which is the sigma squared, which is what that is, that symbol, equals the summation of each observation minus the mean, and that's the population mean, squared divided by the total number of observations. The reason we need to understand variance is it will help us get to a very popular measure that we need to understand for variability, which is standard deviation. You probably have heard standard deviation throughout working with data, working with reports, or just you may have heard it on the news, you may have heard it in class, different places. Well, standard deviation used to be a hard thing to understand until I really got into understanding what variance is. Then I understood what standard deviation is. So standard deviation simply, mathematically, is the square root of the variance. That's all it is. So all the stuff that we just figured out as far as figuring out what the variance is in a set of data, all we do is take the square root of that and we end up with the standard deviation. So for the sample, it's represented by the letter S. So it's S equals the square root of S squared, which is the variance for the sample. And the population there, it's sigma, which is equal to the square root of sigma squared, which is the population variance. The coefficient of variation is another measure that we want to take a look at. You take the standard deviation and divide it by the mean and multiply it times 100, and you use that as a percentage. And what it does is it measures the standard deviation relative to the mean itself. As we continue to analyze distributions in this review of descriptive statistics, one of the things we want to make sure we remember is that there is something called a percentile. Now, you've taken a standardized test, and you know from those standardized tests that you may have scored at a 50 percentile, a 90 percentile, an 80 percentile. And the main thing I want to say about percentiles is that it does not represent your performance. What it does is it represents your score versus every other score that has been captured. I remember when my children came to me once they took I think it was called the MCAT test or the standardized test in elementary school. And one said, hey, I think I got an A. And I was like, what do you mean? He said, well, I got 90 percentile. I was like, well, that's not an A. And of course, I had to quickly explain why it wasn't because I saw the tears start to well up in her face. And I said, no, here's what it is. You did very well, but what it represents is your score on the test is at the level where it is as much as what 90% of everybody that took the test did. So you did just as well as 90% of everybody that took the test. And of course, the change in emotion that quickly followed that statement was very satisfying, because what came back to me as a dad was, oh, so I did just as good as 90% of the people that took the test when I took it? I said, exactly right. So percentage and percentile is really that. How well your score is compared to everybody's score that was captured at that moment. Just like you have percentiles, you also have quartiles. Quartiles is where you divide the data into 4 equal parts. Each part contains approximately 25% of the observations, and the division points are referred to as quartiles. So you can have a first quartile, a second quartile, a third quartile, and a fourth quartile. Now, Q1, the first quartile, is the 25th percentile. So that would be all of the data that fits between 0 and 25 percentile of the data observed. The second quartile would be the 50 percentile, or also the median, which we just talked about. So from the 25th to the 50th, that's Q2. Q3 is from 50 to 75. That would be the third quartile. And then the fourth quartile would be from 75 to 100. As we're talking about analyzing distributions, let's talk about another measure that we use, which is called a z-score. The z-score measures the relative location of the value in the data set. It helps determine how far a particular value is from the mean relative to the set's standard deviation. So we learned about standard deviation, what that is. We learned what the mean is. That's a measure of location, where the standard deviation is the measure of variability. And now what we're trying to do is come up with a standard value, regardless of the data, to understand where any data point fits throughout the entire data set. Now, how do we get to this thing called a z-score? Well, what we do is we figure it out by taking the observation and we subtract the mean and we divide by the standard deviation. It's that simple. So z would be the z-score for the observation. You would basically take z, and that would be equal to the observation, which is x sub I, minus the mean, which is the x with the line over it, divided by the standard deviation. Table 2.13 helps us with figuring out z-scores for for the class size data. Remember the example where we had a class size of 46, 46, 42, 54, and 32? So now what we want to do is figure out what the z-scores for each one of these would be. So the mean would be equal to 44, and the standard deviation would be 8. As you look at the chart, these are the z-scores for the class size data that we've been working with so far. As you look at that chart, you see that 46 has a z-score of 0.25. 54 has a z-score of 1.25. 42 has a z-score of negative 0.25. 46 has a score, again, of 0.25. And 32 has a score of negative 1.50. Now, you may be wondering, okay, now that I know what the z-scores are, what do they really tell me? Well, here's what they tell you. A z-score of 1 is equal to 1 standard deviation. A z-score of negative 1 is equal to 1 standard deviation below the mean. So based on the z-score calculation, what you're basically doing is trying to place the value of the actual observation on a bell curve, so you know exactly where it is as it relates to the overall data that you're measuring and how far it is from the mean. That's going to be very important down the road. So remember that the z-score is basically normalizing the data and the observations so that regardless of what data you have, you know where that data sits in the bell curve as it relates to the observations. Here's how we can use the z-score. As you think about what's called the empirical rule is used for data having a bell-shaped distribution. If the data is within 1 standard deviation, it is basically representing 68% of all the values. So 1 standard deviation on both sides of the mean represents 68% of the data. 2 standard deviations from the mean represents 95% of the data. 2 standard deviations above the mean, 2 standard deviations below the mean. That's 95% of the data. And then the last one, 3 standard deviations on both sides of the mean, represents almost all data values. Why is this important? It's very important because you want to make sure that your data fits into this type of framework so that all the things you're going to say about it using these different tools are pretty accurate. If you're familiar with the term Six Sigma, basically 6 sigma is 6 deviations above the mean and 6 deviations below the mean. So everything around that topic is around how do I drive efficiency so that I can get as much as I can from the data or from the process that I'm working on. And that's how it came about using this concept. You can have outliers. Outliers are extreme values in a data set, and based on where they sit on the z-score or where they sit on the curve, they can pull your data and your observations and their measures one way or the other. That's why we also study skewness, to make sure that if data is skewed, we take into account what we have, and maybe we need to grab another sample, grab more data from the observations and what's available to us in order to make this work better. Once we have the quartiles, we can now look at a graphical representation called a box plot. It's one of my favorite ones to look at because once you have all of the quartile information and you plot them, it kind of gives you an idea of where the data sits that you're measuring. So it's just basically a graphical summary of the distribution data that starts with your Q1 quartile, that's represented with a line. Your Q2 quartile is represented with a box. Then you have your median. Then you have a Q3 quartile. And then you have another line representing your Q4 quartile. You will see the box plot represented in a lot of ways. One of the favorite ways I've seen it represented is in a stock picking chart. So if you look at stocks and you look at the close, the open, and the movement of the stock, usually they are represented in this way with box plots. Here's a box plot in figure 2.22 of the home sales prices that we were measuring a little bit earlier in another example. You see in 5 different suburbs, and these are suburbs of Cincinnati, Ohio. you will see the quartile information for each city represented in the box plot. One of the observations from looking at this chart is this. I see that in Irvine, or Irving, depending on where you're from, that the spread of the data in the quartiles is a little different. And also, if I look at quartile 4, it's a very, very long line. Well, what that means is that one of those home prices is way up there, maybe closer to 400,000, where a lot of the other home prices are a lot lower. So that's something you would want to pay attention to when you're studying quartiles and you're studying box plots. Versus if you look at the one in Hamilton and the one in, I guess that's Groton, those box plots are smaller, which means that the data is closer together, whether it's the Q1 data, the Q2 data, the Q3 data, or the Q4 data. Because of the size of the box, the data is closer together in those areas, which means the home prices are pretty comparable versus in other places where you would have a wider range. There are measures that you can look at that help you with the association between two variables. One way to see those different relationships is by using something called a scatter chart. Think of an XY chart and basically plotting the observations based on those two variables. You've done those as early as middle school from a math class perspective. But now we want to use them in order to see if there's a relationship between the variables. One of the things we have to look at in observing scatter charts is covariance. And what covariance really is the descriptive measure of the linear association between two variables, the linear association. To calculate the covariance for a sample size of n, in other words, whatever number of observations you have, you basically do this. You take each of the observations, which should have a y and an x coordinate, and you take the x coordinate of the observation, you subtract the mean of all the x coordinates, then you multiply that times the y coordinate for each observation, and you subtract from the y coordinate the mean of all the y coordinates. Once you do that for each observation, you sum each of those and divide it by the number of observations minus 1. Now for the population covariance, you do the same thing, except you divide by the number of observations. That gives you a descriptive measure of how the association between the variables is related and how linear it is. Something else that can help us with this relationship between the variables is the correlation coefficient. This one you may see a lot more as you do more descriptive statistics. It measures the relationship between the two variables. To calculate the sample correlation coefficient, what you do is you take the sample covariance, which we just talked about, and then you divide it by the sample standard deviation for the x-axis, or all the x components of each of your observation, and you multiply that times the sample deviation of the y components of each observation. You end up with something called R. Now, R is an interesting measure for you to learn about as you try to relate different variables in data. In fact, here's how we interpret the correlation coefficient. If the R value is positive and greater than 0, the closer you get to 1, the number 1, it has a very positive linear relationship. Now, if that number is less than 0, the closer you get to -1, it has a very strong relationship, but it's a negative linear relationship. The closer that R value gets to 0, it means that it has no linear relationship. Let's see if we can make up an example for you. I like going to a popular ice cream parlor called Grand Old Creamery on Grand Avenue here in St. Paul, Minnesota. The number of times that I go to the Grand Old Creamery parlor after church on Sunday is probably highly related to the number of times that I go to church on Sunday. Why? Because the Grand Old Creamery parlor is a block from my church. So I could say that there's a positive correlation between the number of times I go to church and the number of times I go to the ice cream parlor. Basically because of how close they are. But if I tracked all of the times I went to the parlor and all of the times I went to church, there would be a relationship giving me a result with an R that is close to 1.